So here's the first question. We were looking last lesson at using integration to work out the area under curves. Okay? And so here is a question. There's no limits in this question. We're just told to find the area of the region bounded by that curve. Well, we've got a calculator. Why don't we sketch this using the graphing function on our calculator, just to see if we can understand what it means. So I've written it up there so I can do the same. Are we all calculated up today? Good. So so remember you got, yes. You mean batteries, do you? You've got two options for sorting out your axes. So V window and standard is a good sort of starting point, and then you've got your plus and minus and your cursors. And so I hope that when you see that, you should say, oh yeah, cool, I know, I should have known that, because I know when I multiply that, it's going to be a quadratic, and if I asked when was this equal to 0, then x is 0 and x is 3 would be the two solutions, the two roots. So I know that it's going to be a graph like that goes through 0 and 3. But of course what we're talking about in this example is not an area under the curve. The area, if we return to the question, the finite region bounded by the curve and the x-axis, we're talking about this region here. It's the area above the curve. So let's just do this integration using the technique that we introduced last lesson. So this is where we are using limits. We're going to use the limits of 0 and 3. So we're going to integrate this function with respect to x between 0 and 3. Before you do anything, multiply out the brackets. And you can have a go at talking Macy through those steps that we do. Have a go. Have a go. That's you're going to notice something with your answer. Okay?
You can do each of them.
That was the sort of framework we were using, wasn't it? So once you've integrated, substituting x is 3 and gives you the area up to the 3 value. Substituting 0 in gives you the area up to 0. And so one take the other gives us the area that we are after. So we are increasing the power by 1, dividing by the new power. do you remember, use your calculator to do the substitution, because that's where the mistakes nearly always occur. So I'm going to make x equal to 3 in my answer. And then I can go back up and replace the 3 with a 0, except I already know when I make x equal to 0 in that it's going to be 0. And where's the plus c? Well, of course, we've got a plus c here, take away a plus c there, so they've disappeared. So although I write a plus c there, I don't bother writing it there. Yes, Oliver?
Because it's an area, does it matter, because it's below the x-axis, does it matter whether it's negative or
Well,
positive?
You've noted the difference in this answer to all the answers we had in our last lesson. Our answer is negative. And the reason it is negative is because we're dealing with an area underneath the axis rather than above the axis. So how big is the area? Well, it's 9/2. It's 4.5. So the area is 9/2. The fact that it's negative is because it's the area underneath the axis, and the way that integration works, areas underneath the axis will always appear as negative. And so in that case, you sketched it on your calculator, so we were expecting an area under the curve, and so we're okay. We're okay. We knew that was going to happen. It didn't throw us. It didn't throw us. If you went to a rubbish school and you weren't very good at recognising a quadratic, it might have thrown you a bit, but it's not going to throw us. But there is an implication. There is an implication that we need to be aware of this whole negative area thing, and I can demonstrate it with the second example. So I hope you recognise this as a cubic. Can I get you to either sketch it manually if you want, working out where the roots are, or use your calculator. I'm going to use my calculator, but see if you can sketch this one, and we're going to see if we can do the same thing. I've written it on the old board.
What were the arms of integration?
It's just the finite region contained between the graph and the x-axis. So I'm hoping when you saw that graph you said, oh yeah, of course it looks like that. It's a cubic. If I multiply that out, I'm going to get a cubic. And its roots are 0, +1 and -3. We don't know how high that is and how low that is. We use differentiation to find that. It's not really relevant. But the issue is that the area enclosed between the graph and the x-axis comes in two chunks. We've got this area here and this area here. And don't forget that if we worked out this area here, it would be negative. So this means that if I worked out that area by integrating it and substituting in -3 and 1, I'm not going to get the correct answer, because what I would get would be this area and this negative area, which would cancel out a little bit of that. So the answer to that would be that area with that little bit lopped off, not the correct total area. So when I get an integration like this, which is broken into two areas, that isn't going to work. Instead, what I've got to do is I've got to do it as two separate integrations. That one, from -3 to 0, I know is positive. This one, from 0 to 1, I know is going to be negative, but I'm going to ignore the sign and just take its magnitude, its size. So we have to do this as two separate integrations. So here we are in another situation where we've got a big advantage with our calculators, because we can have a look at what they actually look like just to confirm whether or not we've got this sort of situation. And when we have to adjust our approach. So go on, have a go at working out those two integrations. No one's smoking, are they? I can smell smoke. It's not in the corridor.
It's like coast.
Sorry?
It smells like toast.
It smells like toast.
Burnt toast.
Oh, toast.
It could be toast.
I think I'll avoid hitting the fire bell just yet. I think we're even worse if you let. We'll hope it's... Yes, Ben?
Wait, so are you trying to work out the two areas? So for the
Yes, yes. So the two areas are these together.
It is.
Of course, you're going to have to multiply out the brackets. Yes.
Would it be the 0 minus 3 in the bracket?
Say again, sorry.
So you know when you write out, it would
Yes.
be like...
So yeah, so the bigger number,
First one.
the first bracket is always the biggest number. Yeah. So you're going to have, so you'll multiply it out, you'll get your answer. So yeah, you're going to substitute in zeros first, and then -3. So it's always that number that you put first, followed by that number. Because the good news is you've only actually got 3 values to substitute in. I mean, actually 0, we know what's going to be anyway. But remember, I know that this one's going to be negative, and I'm going to ignore that. I'm just going to take its magnitude. I'm going to add the two magnitudes together to get my final answer. And we don't use a unit, we just give the answer as a number. So having substituted in -3, and that would have been a nightmare without this method, I could just go up here and edit that and turn it into 1 plus 1. I was expecting that to be negative, so I'm not fazed by that, and that means my area is 45/4 added to 7/12. 45/4, that's 135/12, added to 7/12 is 142/12, hopefully. Let me check. Which is 71/6, yeah. So you've just got to be careful with these integrations, particularly ones where they haven't drawn a picture for you. Just be careful that it's not one of these ones where you've got some above and some below. If it's all above or all below, you can do it as one. But in questions like this, you have to do it as several different bits. So let's just practice that. Textbook page 301, 302. This is in the Pure 1 book. I'll give them that in a minute. 301, 302. Question 2, which is on one page. Question 3, and then question challenge 2, which is a good one to have a look at. So for those at home, that's page 301 and 302 in the Pure 1 book. Question 2, which is on 301, and question 3, which is over the page. So here's where we are going today. We're going to work out the area of shapes, not under a curve necessarily, but shapes between curves and straight lines, or between two different curves. And we're going to use integration for that, to help along with other techniques here. So here's my first example. We want to work out this yellow shaded area, and it's the area between a straight line, y equals 2x, and a curve, y equals x times x minus 3. I'm going to multiply that out straight away just to make it nice and easy. The yellow area clearly isn't the area under the curve, and yeah, this curve, if we wanted to work out the area enclosed between the curve and the x-axis, we'd have to do it as two separate areas. We know this one will be negative, we'd ignore the negative. That's what we did on Friday. No, this is not that at all. That yellow area is, well, could anyone explain how I could go about finding out that yellow area? I mean, it starts with something from primary school, and then we use a little bit of integration to help. What do you reckon, Harrison?
Huh?
What do you reckon?
I reckon you could probably find out the area from the graph from A to B.
Right, okay, so certainly it looks like this area here, so nothing to do with this area, but the area underneath the curve from A to B, that looks like it might be helpful. That area under that curve, let me shade it in, recalibrating, okay, this area here, that's not part of the yellow area. So can anyone complete the picture and suggest how we can use, that's integration, that's not from primary school, is it? So the other thing must be something from primary school. Which reckon on
The area of a triangle.
it? It is, yeah, yeah. This triangle here that goes up to B and up and then down the red line, that triangle there, if I work out that area, base times height divided by 2, and subtract the area under the curve, that's going to give me the area that I'm after. So the yellow area is the area of the triangle minus that little area there. Now we've got some information missing, haven't we? Firstly, we've got the value of A, which is one of the two roots of the curve. So what do you reckon, Harry? What's the value of A? I can tell that just by looking at the curve. What do I know one of the roots of that curve will be? X is 0 is one root. 3, yeah. So I know that A, well, I know A is 3. What I don't know is where this value here is, although I note it's where the two lines cross. So it's where y equals 2x intersects with y equals x squared minus 3x. That's a simultaneous equation problem, isn't it? Asking when does that equal that? They're both written as y equals. So go on, have a go. See if you can get somewhere with this. I mean, ironically, this is probably the easiest bit because we know so little about the triangle. But yeah, have a go. Area of the triangle, base times height divided by 2, and then take away the integration area, and that gives you the yellow shaded area. Let's have a look at this. I'm going to pause the video while we have a go. Okay, so I solve the simultaneous equations, and I get that the two lines cross when x is 0, when x is 5. Well, yeah, they cross when it's 0, so that means B must be 5. And that means I can fill in this here, but it also tells me the base of my triangle is 5. When x is 5, if I go back to y equals 2x, that's probably easier than substituting it into that. The y value is twice that, so that means it's going to be 10. So the coordinates of this point are, of point C are 5, 10. Clearly the graph is not to scale, but that means that that is 5, 10. So we've got area of the triangle, 5 times 10 divided by 2, base times height divided by 2, which is 25. And from that, we're going to subtract the answer to our integration. Here's one I prepared earlier. So I increase the power by 1 divided by the new power, increase the power by 1 divided by the new power, substituted in 5, but I didn't. I've got my calculator to do it. Then substituted in x is 3. I've got my calculator to do it. And so that's the calculation, and I'm going to be very lazy and hope that hang on a minute. Oh, sorry, wrong example. That's a relief. Yes, there we go. So it's quite a clever skill, isn't it? Yeah, combining areas that we can work out using the shapes that we know the area of, and also our newfound skills of integration. Now actually, you didn't need to have done it that way. So if we go back to the original problem, the area of the triangle, and it's by far the easiest way to work out as the area of the triangle, but the area of the triangle is also the area under y equals 2x. So an alternative would have been to say, right, let's integrate 2x, and that's between 0 and 5. So I could have done it as an integration. I would have got exactly the same answer, 25. You would have got 2x squared over 2, which is just x squared. Substitute the values in, and that would have given you the answer. However, much, much, much easier to do this as an area of a triangle, and hopefully you'll agree that in the subsequent questions we're going to do today, working out the area of a shape using those shape formulas that we learned at primary school are going to be a whole lot easier. So, we are on page 304, page 304, and I think the first 3 questions in this exercise are definitely worth doing. The third one is a little bit fiddly, but we're up to it. So that's exercise 13G. Unfortunately, it's not letting me draw on the board, but I hope you can see that these 2 points here are plus or minus 2. And that means if I draw a rectangle here, that's going to go from -2 to +2, so that's got a length of 4, and I already know the height of that rectangle is 6, so again, not drawn to scale. So the area of the rectangle is here. From that I need to subtract the area under the curve between those 2 points. So I need to work out the area under x squared plus 2 between -2 and +2. So the rectangle minus the area below the curve leaves me with the yellow area. Like I say, we're working through this exercise, so finish that one off and then carry on. So I integrated, substituted in 2 and -2. Again, get your calculator to do that, because substituting in negative numbers in particular is really fraught with mistakes. So that gives you 40 over 3, so you get left with 24, which is the area of the rectangle. Take away the area under the curve, gives you 32 over 3, or 10 and 2/3. Okay, carry on through the rest of the exercise.